Hello, everybody. This is Sunday. It's July 3rd, and we are heading into week 9 of our online astronomy course. Now, before we start talking about week 9, I want to remind you that this coming week is when you're going to be taking your second exam. The second exam opens up tomorrow. That's July 4th. That's a holiday, but you can still take it if you want to. And it will be open until next Sunday, which is July 10th. So anytime in there, you can take the exam. Remember, you can take it twice if you want to. You don't have to, but if you do, I'll give you the average of your 2 scores. And it is open book exam. You can use your textbook. You can use the homework quizzes that you've been doing, but no other resources are allowed or permitted or even needed, I think. You're welcome to have a calculator by your side if you want. You're not going to need it, but if you want to have it there just for security, that's just fine, and you're welcome to use it. Okay, we are done with the planets. We're done with the solar system. And in Module 9, we're going to start talking about the stars. And the star that we know most about is our own sun. So what is our own sun like? What is a star? What is our sun? What is it made of? Is it solid? Is it burning like wood in a campfire burns? And the answer is that the sun is a big ball of gas. There's no solidity to it all the way through. It's gaseous. And in fact, it's a sort of a gas called a plasma. And that is that the sun is so hot that the electrons have been removed from atoms. The electrons are still there in the sun, but they're just not attached to the nuclei of atoms. So if you took a handful or you took a big bunch of the sun and you had like 100 kilograms of the sun, 71 of those kilograms would be hydrogen. And another 27% would be helium. And only 2% would be the heavier elements, heavier than hydrogen or helium. So the sun is a big ball, mostly hydrogen, but quite a bit of helium in there, but then the rest of the elements are only 2%. The second thing to know about the sun is that it's huge. It's huge. And here behind me, you can see the curved surface of the sun. And right up here is Earth. So you can see how small Earth is compared to the sun. And in fact, if you could hollow out the sun, just make it hollow, and you were going to drop in these Earths, how many would fit in? 1 million Earths, over 1 million Earths would fit inside the sun. That's how huge the sun is. So it's this big ball of hydrogen and helium, very hot. It's about 5,770 degrees Kelvin. That is degrees above absolute zero. We're using the Kelvin temperature scale in this course. So it's 5,770 something degrees above absolute zero. At the center, it's more like 15 million degrees. At the center, it's really very, very dense. On the whole, the sun on average is not much more dense than water. It's about 1.4 grams per cubic centimeter. Water is 1 gram per cubic centimeter. So the sun overall is just a little bit denser than water. But if you get down to the very center where the gas is really compressed, it's over 150 grams per cubic centimeter. It's very hot down there, as I said, about 15 million degrees. And so what powers the sun? You know, the sun has been shining for something like 5 billion years, roughly. So where does that energy come from? A long time ago, people thought it might be burning, like wood burns or coal burns. but there's just not enough coal there to power the sun for all that time. And today we know it's a nuclear reaction that powers the sun. And that nuclear reaction involves 4 hydrogen nuclei. Now, the center of a hydrogen atom is just a proton. So what happens is that 4 protons all combined, and they combine together, and they form a helium nucleus. Now, a helium nucleus is sometimes called an alpha particle. So later in the course, we'll refer to it as an alpha particle, but right now we'll just call it a helium nucleus. So what happens is that 4 protons, 4 hydrogen nuclei come together to form 1 helium nucleus. Now, you might think, well, how does that produce energy? And it turns out for every 1,000 kilograms of hydrogen that go into that reaction, only 993 kilograms come out. So there's 7 kilograms missing. Where did that go? You know, you can't just get rid of mass. And what happened to that 7 missing kilograms is that it got changed into energy by Einstein's equation, E equals mc squared. Einstein's equation says that mass can be converted completely into energy. And the conversion factor is c squared. That is the square of the speed of light. Now, the speed of light is a big number. It's like 3 times 10 to the 8th meters per second. So c squared is like 9 times 10 to the 16th. So if I put in a little bit of mass, that can release a huge amount of energy. And in fact, in 1 second, the sun releases enough energy to supply Earth's energy needs for 800,000 years. That is how energetic these nuclear reactions are. And what happens is that, as I said, 4 protons come together, 4 hydrogen nuclei come together to form a helium nucleus, and that is the power source of the sun. That reaction is called the proton-proton chain because really they don't all come together at the same time. 2 come together, and then a third, and then a fourth in a chain of reactions. And so it's called the proton-proton chain, linking together those 4 protons to form a helium nucleus. So the sun is an amazing object, and it's the source of all our light and heat and energy on Earth. Even fossil fuels, our energy comes originally from the sunlight that warmed Earth billions of years ago and allowed plants to grow, which decayed in swamps to form the coal and the oil and other things. The sun is huge. There are these huge, the sun has a magnetic field, just like Earth does. And the plasma, that hot gas in the sun, is channeled along the looping magnetic field. And I'll just move to the side here so you can see it. Here's a flare that's leaving the sun's surface. And you can see it here. It loops up from one side, and then it moves around to the other side. And take a look at the size of our Earth compared to the size of those loops. You know, it's really just amazing. So you'll be learning all about the sun, what it's like. You'll be learning about the sun's atmosphere. The sun does have an atmosphere. That's a layer of cooler gas that's lying on top of the sun's surface. And you'll learn how that layer of cooler gas, if you remember Kirchhoff's laws for light, how a cool gas that's overlying a hot, dense gas can form dark absorption lines. And from those dark absorption lines, we can learn all about what the sun is made of. We can also, believe it or not, peer inside the sun because the surface of the sun is vibrating. Just like earthquakes on Earth, there are sunquakes on the sun. And just like on Earth, we have seismology. That's the science that analyzes those earthquake waves, how they move through the Earth, so we can see inside the Earth and know how the Earth is structured. On the sun, we have helioseismology. Helio, from the Greek sun god Helios, but helioseismology lets us see inside the sun and know what the sun is made of and how it's structured. So I really hope you'll enjoy learning about the sun. It is a fantastic object. It is 93 million miles away from us, to use miles here for a second, and we can still feel its heat on these hot summer days. It's really fantastic. Before I go, I will pull up Stellarium here just to see what's going on in the night sky this time of year. So let's take a look. Here we are, there's Stellarium. This is set for July 7th, and so that is this Thursday. That is the date of the first quarter moon. We're out here, we're facing south, southwest, and it's around 10:30 at night. You might recognize Scorpius over here. Here's the Scorpion's head. Here's the red giant star Antares. Here's the Scorpion's body going down, and there is the stinger in his tail. And I'll just put up the lines here so you can see Scorpius. Now, you know, I show you these lines, but these are the lines that are recognized by astronomers. These are the constellations according to the International Astronomical Union, and they're the that's the international group that decides where the boundaries of the constellations are. And you can see the constellations of the Zodiac here. Here's Virgo, Libra, Scorpius, Ophiuchus, Sagittarius. Yes, some of you were born in the when the sun was in the constellation of Ophiuchus. So I guess astrologically you're Ophiuchoids or something like that. But these are the Western constellations. But it's sort of interesting to take a look at what other cultures saw in the sky. And so I'm just going to take a quick look at what the Navajo people saw in the sky, because they too saw patterns in the stars and told stories about them. And so over here in the southwest, there's man with feet apart. And due south is the first big one. And that's, you can see the constellation, our constellation of Scorpius makes part of the first big one. And here, what I was calling the stinger in the tail of the scorpion, the Navajo would refer to that as rabbit tracks. So I think it's just really cool. And if you're interested in things like this, you can go to this left-hand bar in Stellarium and click on it. And there's all these cultures that you can learn about, and there's external links here that will tell you some of the stories that are associated with those constellations of other cultures. I'll just go back to the Western constellations now. So I will, a little bit later today, I'm going to send out an email to everybody just reminding you to take the exam this coming week. It's 35 multiple choice questions, exactly as they were before. You take it on Canvas. You'll find the exam right after Module 8 and right before Module 9. The exam is right there, and you can take it anytime during this coming week. If you have any questions, you're welcome to ask. Just send me an email. Be happy to set up a Zoom meeting or meet in my office if you'd like to. And I hope you have a safe 4th of July weekend. Be careful of the drought. Try to respect our friends, our animal friends who may not like fireworks, and have a great week. And I will look forward to seeing you next week. So until then, have a fine week, and I'll see you then. Bye-bye.